Every function you have ever written returns one answer. An LLM returns a different one every time. That difference breaks every reliability assumption your engineering career is built on. In 10 minutes, you'll know why. In the last video, we traced 12 years of AI history, AlexNet to ChatGPT. Every system we named is different from the software you have probably spent your career writing. Today, why? You are a software engineer, you write a function, you test it, it passes, you ship it. That's been the job for decades. Same input, same output, same test, ships every time. Now you add an LLM call to your code base. Maybe it's just classifying your user's message. Simple thing, right? You write the test, run one passes, run two fails. Pause here for a second. Was that a bug or was it working correctly? Let's go back to function. The mathematical idea of a function is simple. One input maps to one output. Always, no exception. Sort 3, 1, 2 returns 1, 2, 3. Not sometimes, it is always. This property has a name, determinism. A deterministic system guarantees the same output. For any given input, run it once, run it 10 times, run it a million times. It's always the same answer actually. Traditional software is entirely built on this guarantee. Your if statements, your database queries, your payment processing logic, all functions in this mathematical sense. That guarantee is what makes unit testing possible. You know what the correct answer is. You hard code it, you run it, you check it. That's the whole system. But what about random numbers in a traditional software? Good catch. Even random runs on a deterministic seed algorithm. The seed changes, the sequence doesn't. Here's what this guarantee actually buys you. One test line. Asset sort 312 equal to 123. Not just today, not just on your machine. The assumption is that the fact about the function. It passes in staging, it passes in prod, it passes in 10 years. Pass here. Think about how much of your job exists because of that guarantee. Code review, CI/CD, pull request check, automated deploys. All of it assumes the function doesn't change its behavior between environments. This is so deeply embedded in how you think that you don't even notice it. It's like the water you swim in. Hold that thought because we are about to break it. Here's what it clicks. An LLM doesn't map an input to an output. It maps an input to a probability distribution over outputs. Here's what that means. When you send a prompt, the model is computing. Given everything in my context, what's the probability of each possible next token? For the capital of the France question, the model might assign 85% probability to Paris with a capital P, 8% to all small letter Paris, 4% to all capital Paris, and distribute the rest across hundreds of other tokens. Before I keep going, predict what happens next. Does it return Paris with a capital P because that's the highest, or something else? Think about it. It just doesn't return Paris with a capital P. It samples from the distribution. Most of the time, you get Paris with a capital P. Occasionally, you get Paris with all small letters. Rarely, Paris with all capital letters. The sample is stochastic. That's not an accident. Randomness is the future. That's how the systems produce creative, flexible output. You can't optimize that away. If you set the temperature to 0, you suppress it, but you lose the flexibility that makes the model more useful. Let's make this concrete. Take the prompt. Explain photosynthesis in one sentence. Run 1. Photosynthesis is the process plants use to convert sunlight, water, and CO2 into glucose and oxygen. Run 2. Plants capture light energy to build sugar molecules from carbon dioxide and water, releasing oxygen as a byproduct. Run 3. Photosynthesis transforms solar energy into chemical energy stored in a glucose using CO2 from the air and releasing O2. Which one is wrong? Pass and decide before I answer. None of them right. All three are correct. All three are good. None is the right answer the way. Sort 312 has the right answer. The model didn't make a mistake three times. It gave you three valid examples from the distribution. This is the shift. Now watch what happens when you try to unit test an LLM call. You write asset summarize long article equal to expected summary here. Run it 10 times, 10 different summaries, all valid, all different, your test fails 9 of them. You might think, I'll test whether the key facts are present. Better. But now you are evaluating with another LLM. uh, and that introduces more probabilistic uncertainty. You can't test a AI the way you test functions. Not because AI is broken, because it is fundamentally different thing. Your mental model, input, test deterministic functions, output doesn't apply here. Here's the free frame that changes everything. The correct way to think about a model called ascent f of x equals y. It is probability of y given x. The probability of output y given input x, that's the object you are working with, not a value, a distribution. This might feel like a subtle notation change. It isn't. Try this. How would you test probability of y given x? What would be passing test look like for a distribution? Think about it before I answer. You don't test it with assertion. That hard code one correct output. You evaluate it with expectation across many samples. You set an acceptable range. You measure whether outputs fall in the right distribution. You run evals, not unit tests. That's the engineering shift. Not harder, but it's different. In the last 10 minutes, we have watched the foundation of traditional software engineering, the deterministic function, get replaced by something else. Not worse, but it's different. The engineers who struggle with AI are the ones who keep trying to force it back into this functional model. They add retry loops, chasing a consistent answer. They hardcode expected outputs. They treat every variation as a defect. The engineers who thrive accept the distribution. They design for it. They test for it. They build an evaluation system that reasons about population of outputs, not an individual sample. One sentence that will separate you from 90% of the people talking about an AI. We are not debugging a system. We are characterizing a distribution. Say that in your next settings. Watch what happens. Traditional software of f equal to y is not the right one. In AI models, the probability of y given x not worse, just different. Next, we map the entire AI landscape in 2026, who's building what, which models lead which benchmarks, and where the real competition is. See you there.